Ooh, boy, it's cramped in there. Let me get a good stretch in. Ugh. Oh, greetings, mortal. My apologies for the sudden appearance, but be not afraid. You have rubbed my lamp, and in so doing, finally released me, an honest-to-goodness genie, from my centuries-long confinement. Allow me to offer you a token of my gratitude, 3 wishes of your choosing. If you seek wealth, power, love, fame. I'm sorry, you said you wish to know how to graph quadratic equations in intercept form? Not world peace? No more bigotry? An end to world hunger? You sure? Well, okay then. If you wish it, then so it shall be done. Welcome to Class 3 of Unit 8, Quadratic Equations in Intercept Form, Part 2. Now, last time we were together in class, we introduced the intercept form of a quadratic equation in 2 variables. Take 30 seconds, pause the video, look back at those notes. What is intercept form? Where does it come from? And why is it useful? What does it tell me about my graph? Go! Alrighty. Well, intercept form is really just a fancy way to say that I take my standard form and factor it. When I do, I end up with something that looks like this, some constant potentially at the front, we'll call it a, times some second factor x minus p times some third factor x minus q. The idea, of course, is that if I were to take this equation and plug in 0 for y, I could use the 0 property to solve for each of those values of x. Of course, plugging in 0 for y gives me the x-intercepts of my graph. So what this tells me, of course, is that if I were to take each of those factors and set it to 0, that value p from the first one, comma 0, and that value q from the second one, comma 0, would give me the x-intercepts, right? The place where I cross my x-axis. Cool. Now that we've got it, and perhaps more importantly, now that we know where this form comes from and why it's useful, let's get a little practice using it to graph some parabolas. Now I'll tell you, there are 4 steps to the procedure of graphing a quadratic equation in intercept form. Take a minute, take a chance. Who cares? Pause the video. What do you think some of those moves might be that I want to make as I'm building out my graph? Go! Alrighty, let's see if we've got any whammies. Well, first of all, important to remember, I need at least 5 key points on the graph of a parabola, just like I would 3 on the graph of a line. Of those points, the easiest first thing for me to do if I'm already in intercept form would probably be to find my x-intercepts. Of course, the way that I would do that is by setting each of my factors to 0 and using the 0 property after setting y to 0, right? If I'm on the x-axis, y is 0, I have not gone up or down. From there, you'll remember, hopefully, that we used the symmetry of our graph to notice that our vertex lived halfway between our 2 x-intercepts. What's the fancy mathematical way to say that a value is halfway between 2 other values? Go. 5, 4, 3, 2, 1. Well, hopefully you will remember, right? An average is a fancy way to say that I want the midpoint of 2 values. So the important thing for us to take away here is that the x value of our vertex, if it's halfway between our x-intercepts, its value should be the average of our x-intercepts. From there, right, I can plug into my original equation to find the value of y. There's my point. From there, I need 5 points in total. I've got 3. I need to find 2 more. But we can be strategic about the points that we find. The hint that I'll give you is that when it's possible, we will need to find an additional point anyway when identifying our characteristics. That point, of course, is going to be our y-intercept, right? That's one of the characteristics that we need to identify. Of course, the way that I find my y-intercept, if I'm on the y-axis, is that I need to plug in 0 for x. When I do that, knowing that my graph is symmetrical, I can use the symmetry of my graph to find the companion point on the other side of my axis of symmetry to the y-intercept I've identified. Last but not least, I've got my 5 points. Connect them with a parabola, just like I draw the line through my 3 points back in Unit 4. There you go. There's your graph. Very cool. With this strategy in mind, again, we don't need to use it religiously, but it could help guide us through the process of graphing something like this. Y equals negative x plus 2 times x minus 4. Use that procedure. Give yourself a good fighting chance. See how far you get. Pause the video. Once you're genuinely stuck, come back and check with me. Let's see how far we can go in building our graph and identifying its listed characteristics. Go! All right, you ready? Let's do it. So for my x-intercept, probably the wisest place for me to start, of course, the way that I find it, I like to be really explicit. I'll write it down every time. Let's plug in 0 for y. So I want to take my equation above. I'm going to swap out y for 0 and solve for x. Here, using the 0 property, because my right side is already factored, I can set each of these factors to 0 individually. So at the front, that invisible -1 could be equal to 0, or the x plus 2 in the middle could be my 0, or the x minus 4 on the right could be my 0. Of course, for the first option, -1 can't equal 0. That don't make no kind of sense. I'm going to ignore it. X plus 2 equals 0. Again, skipping some steps here. Subtracting 2 from both sides would reveal that x could be -2. If x minus 4 equals 0, adding 4 to both sides, x could be positive 4. But again, I don't just want x values, I want points. So if the y value is 0, that tells me the points -2, 0 and 4, 0 should live on my graph. Those points, of course, would be 1 over there and 1 over here. I'm being really good, so I'll label those 2 points. Look at that. Step 1 is done. Now that I've got those intercepts, I'm going to use my symmetry to my advantage here. Let's find the values for my vertex. First of all, the x value of my vertex I know is the average of my x-intercepts. The average, of course, I find by adding the values together and here dividing by 2 because I've got 2 values. -2 plus 4 is equal to 2, and 2 divided by 2 is 1. So if the x value is 1, I can now plug into my original equation to find its corresponding value of y. So here y is going to be equal to -1 plus 2 times 1 minus 4. So I've got -1 plus 2 is 3. 1 minus 4 is -3. -3 times -3 is positive 9. So what this tells me here is that the point 1, 2, 3, 4, 5, 6, 7, 8, 9 up for y and 1 over to the right for x should be on my graph. Let me even write it up here, right? 1, 9 is my vertex. From here, I just need to find one more point. Let's be strategic and find the y-intercept. Of course, the way that I find the y-intercept is by plugging in 0 for x if I'm on the y-axis. So here, I'm going to take my original equation, I'm going to plug in 0 for x, and solve for y. So y is going to be equal to -0 plus 2, which is 2, times 0 minus 4, which is -4. -2 times -4 is positive 8. What this, of course, tells me is that the point 0 for x, 8 for y is on my graph. Now, I know that through my vertex lies the axis of symmetry. So I'm going to take this opportunity. Let me draw in my axis of symmetry. I know that if 0, 8 is here 1 to the left of my axis of symmetry, there must be a companion point 1 to the right of the axis of symmetry. The coordinate of this point, well, here this would be 2 over from the y-axis, 8 here from my y-intercept. But I'm actually going to do one additional thing here. To the untrained eye, it might look kind of unobvious where that point came from, so I'm going to indicate right next to it that I used the symmetry of my graph to find it, just so that I know where it comes from. My last move here, I've got my 5 points. Let me, to the best of my ability, connect them with a parabola. And would you look at that? There's my graph. All that's left for me is to identify some characteristics. Well, some of them should be hopefully relatively obvious. As we've talked about before, the domain of any quadratic equation is all real numbers. There is no number that I know that I can plug in here that I wouldn't be able to find a value for. The range, however, here is limited. I cap out here at the value of my vertex. Here, the values of y then cannot go above 9. So there are two ways that I can write that, and again, you're choosing one of them, whichever you prefer. For my set builder notation, I know that y must be below or equal to positive 9, so I could write it like this: y is less than or equal to 9. Or if I prefer my interval notation, right, it can get infinitely small, but the highest it can go, the biggest I can get, is positive 9. I could also take my domain, write all real numbers. If I prefer my interval notation, of course, I could write this as negative infinity to positive infinity. It makes no difference. It's all a matter of preference. For my axis of symmetry, remember a vertical line is always x equals in its equation, right? Y can be whatever it wants, but it doesn't go left or right, so x is always the same. If it passes through the vertex, right, its x value must be 1. This vertex here, it is at the top of my graph. So it is a maximum, and my graph is a sad face parabola. It's opening downward. It's concave down. My last move here is increasing and decreasing. Again, kind of wonky, but I need to use my x values, right, on either side of the axis of symmetry. I'm going up or going down. Here my graph increases, right? If I take my finger and trace along the parabola, my finger moves up on the left side of the axis of symmetry. So for values of x that are smaller than that 1, I would be increasing. So I could write x such that x is less than 1. If I prefer my interval notation, I go all the way off to the right to negative infinity, and then I cap off on the right side. Sorry, did I say off to the right? All the way off to the left to negative infinity, and on the right, I bound myself at that positive 1. Decreasing here is the opposite, right? I'm on the other side here to the right of that x equals 1, so x is greater than 1, or I go from positive 1 all the way off to the right to positive infinity. That wasn't too bad now, was it? Let's do one more practice problem together, and then I'll set you free. Again, you'll notice we're already in factored form. Once we see each other in class, that won't necessarily be the case. Let's find our intercepts, find our vertex. Maybe we can find a y-intercept here that we can use to our advantage. Either way, 5 points in total. Draw our parabola and identify our characteristics. Go, go. Alrighty, let's go. So for my x-intercepts, probably my first move here, I'm in intercept form. Let's plug in 0 for y. So using my 0 property here, 0 is going to be equal to 1/2 x times the quantity x plus 6. I can do some splittage and set each of my factors to 0 individually. So either the 1/2 x is the 0 or the x plus 6 is the 0. For the equation on the left, multiplying both sides by 2 to cancel out that 1/2, x would be 0 times 2, which is still 0. Over here, x plus 6 equals 0, subtract 6 from both sides, x is equal to -6. But again, I'm thinking about points. This tells me here that the point 0, 0 and -6, 0 are my x-intercepts. So 0, 0 is right over there at my origin. And then -6, 0 would be 1, 2, 3, 4, 5, 6 over to the left. Now the interesting thing here, you'll notice that my y-intercept has already been discovered. It's 0, 0. So that's where that if possible disclaimer came from before. Here I'm going to actually need to do some good old plug and chug to find one more point. But before I do, let's find the vertex. My vertex is going to be halfway between these intercepts. So its x value is going to be equal to the average of -6 and 0. -6 plus 0 is equal to -6. -6 divided by 2 is -3. From here, let's find the value of y by plugging in. So y is going to be equal to 1/2 times -3 times -3 plus 6. So this is 1/2 times -3 times 3. We'll end up with a fraction here, but that's okay. I have 1/2 times -3 times 3 is -9. 1/2 times -9 is -9 over 2. So what this tells me is that my vertex, and I'll write it up over here in my characteristics, appears at the point -3, -9 halves. Well, -9 halves, 9 divided by 2 is 4.5, so that'd be 1, 2, 3, 4, and then halfway between 4 and 5, over to the left 3, here is my vertex. Very nice. Now let's find one more point. Again, I can't find the y-intercept. In fact, I've already found it. So I need to find one more value. A hint that I'll give you is that often the nicest numbers come from choosing values really close to that vertex, right? And by extension, the axis of symmetry. So let me take a value of x that's really close to -3. Please ignore the cops coming for me in the back. They'll get me eventually, but not before I finish the video. So I want to pick a nice small friendly number that's close to -3. I'm going to choose -2. When x equals -2, I can now find the value of y by substitution. So y is going to be equal to 1/2 times -2 times -2 plus 6. So this is going to be 1/2 of -2. -2 plus 6 is equal to 4. Half of -2 is -1. So I have -1 times 4, which is -4. What this tells me, right, x is -2, y is -4. So the point -2, comma -4 is on my graph. Now by symmetry, right, I went 1 over to the right and there was a point, so I should go 1 over to the left. There should be a companion point here. Its coordinate would be -4, comma -4. Last move, let me draw in my parabola. We're going to pretend that these lines are straight and perfect and beautiful. There we go. There's our graph. All that's left for me to do is find my characteristics. As always, any parabola has a domain of all real numbers, but my range, of course, the lowest that I can get here is at this y value of -9/2. So the way that I'll write that, and I'll choose to do it in my set builder form here, but you can choose either set builder or interval, whichever you prefer. I know that the lowest I can get is -9/2. So y has to be greater than or equal to -9/2. For my axis of symmetry, it passes through the vertex. The equation of any vertical line is x equals the x value of the vertex is -3. Here, this vertex is a minimum. It's at the bottom of my graph. It's a happy parabola, so it's concave up. I'm increasing to the right of the axis of symmetry, so I'll write this in interval notation. So at -3 is where I start, and then I go all the way off to positive infinity. I decrease to the left, so I go all the way off to the left to -infinity, and then I stop there at that -3.